So this is Chapter 9, Molecular Geometry. Back in Chapter 8, we learned how to draw Lewis electron dot structures, and here's a Lewis electron dot structure of CCl4. And on paper, this Lewis dot structure looks two-dimensional, and it looks like there's 90 degrees between this chlorine and this carbon and this chlorine. But we live in a 3D world, and shapes are determined by bond angles in 3 dimensions, not 2. And so we're going to have to look at some spatial recognition, some 3-dimensional models to help us describe what's called the geometry of different molecules throughout this chapter. And we're going to give names to various angles, and there will be families of bond-angled molecules that you'll get to know really well. So let's look on this page right here, and let's take a look at CCl and what it really looks like in 3 dimensions. And here you can see that the carbon tetrachloride has a carbon at a center, and then each chlorine comes out on the end, and you can see the bond angle is 1.78 angstroms, so they're equal throughout. But then the bond angles actually form the tips of a tetrahedron with 4 equivalent faces and 4 equivalent bond angles. The chlorines want to spread out as far away from each other as possible because the electrons, of course, repel one another, and then it ends up having a bond angle of 109.5. Now, here's a space-filling model of what it looks like. But on your paper, let's see if we can draw it using the space-filling model structure direction. This chlorine is coming out of the paper at us, and so we actually use a wedge to indicate that. We fill that wedge in like this, and we put a chlorine out here. These 2 chlorines go back into the paper, and so we draw them as little dashes like this, and little dashes like this. And this chlorine right here is in the plane of the paper, and so that one goes just as a line like this, and we write it going straight up like this. So that's the 3-dimensional way of showing it, and then we could put a little bond angle right here, and we'd say it's 109.5 degrees. And these angles become super critical and super important throughout this chapter. Alright, there's our 3-dimensional carbon tetrachloride. So throughout this chapter, we're going to learn 5 basic shape families. 5 basic shape families. And each one of these families is based on how one atom is the central portion of it, and then there's several atoms of shared or unshared electrons around it. Here are the names of the 5 basic shape families. There's one called linear, which would have 180 degree bond angles between its central atom and the 2 atoms around it. So this is what it's going to look like in a space-filling model. Trigonal planar, and so every one of these 3 atoms is in the same plane as the middle atom, ends up having a 120 degree bond angle between one atom, the central, and the outer atom. Tetrahedral, that's the one we just talked about. That'll have a 109.5 degree bond angle between an atom, the central atom, and one of the outer atoms. And like we said before, that's the one we drew where this part came out of the paper, those 2 went back in, and this was in the same plane of the paper. And trigonal bipyramidal would be when you have a central atom and then 5 things bonded around the central atom. So this is handy when we have what's called an expanded octet. And this one ends up having 2 bond angles, 90 degrees between the central atom and the atoms above or below, and then 120 degrees for the atoms around the central axis right here. They actually call this middle part, let's zoom in on that one a little bit more, they call this middle part right here the equatorial axis, because it's kind of like an equator. And then these are the axial domains, the top and the bottom right here. And then the last one's octahedral, and you can see that's with 1, 2, 3, 4, 5, 6 atoms around the central atom, and that one ends up having just 90-degree bond angles as well. Everything else that we learn is based on these 5 families of shapes, and these families are known as the electron domain geometries. The electron domain geometries. We're going to break down each one of these families because inside of them there's subfamilies, or there's possible like differences between them, depending on whether they have shared or unshared pairs of electrons around them. And these electron domain geometries will be further broken into actual molecular geometries. So in the next video, we'll go deeply into each one of these families, and we'll look at each one of their subparts and how the bond angles change when they have shared or unshared electrons.